All right, we're back with some more variation of parameters problems. I'm going to pick up with number 7 in the textbook. This one contains a hyperbolic cosine on the right-hand side, and I'm just going to deal with that by the definition of what hyperbolic cosine is. So it says that it's cosh x. Just as a reminder, that's 1/2 of e to the x plus e to the negative x, or 1/2 e to the x plus 1/2 e to the negative x. So we'll deal with that way. And set up our auxiliary equation here. M minus 1, m plus 1 equals 0, m equals 1, or m equals -1. And so our yc equals c1e to the x plus c2e to the negative x. Now, I just want you to know that anytime that you are comfortable with dealing with hyperbolic sine and hyperbolic cosine instead of e to the x and e to the negative x, you can go ahead and do that in place of e to the x and e to the negative x, because, as I just showed, hyperbolic sine and hyperbolic cosine are both linear combinations of e to the x and e to the negative x. So they satisfy this right here. You can probably see that cosh x would already be in here. So would sinh x, which is going to be 1/2 e to the x minus 1/2 e to the negative x. So that's just kind of a fun fact. If you want to deal with it that way, you can. Wanted to make that that statement. So my Wronskian here is going to be e to the x, e to the negative x, then e to the x negative e to the negative x. So this is going to be a -1, and -1 is a -2. And so we're going to get, let's see here, W1 is going to be 0, 1/2 e to the x plus 1/2 e to the negative x, e to the negative x, negative e to the negative x. This is going to be a negative of 1/2 plus 1/2 e to the negative 2x. That is a -1/2 minus 1/2 e to the negative 2x. Okay. And so this is going to be W1 over W is U1 prime. That's going to be a -1/2 times -1/2 minus 1/2 e to the negative 2x is 1/4 plus 1/4 e to the negative 2x. So U1 is equal to the integral of 1/4 dx plus 1/4 integral e to the negative 2x dx. -2 and a -1/2 gives me 1/4 x minus 1/8 e to the negative 2x. W2 is equal to and so this is going to be 1/2 e to the 2x plus 1/2. We have u2 prime is w2 over w, which is going to be a negative 1/2 times 1/2 e to the 2x plus 1/2, and give me negative 1/4 e to the 2x minus 1/4. So u2 is going to be equal to negative 1/4 dx minus 1/4 integral of e to the 2x dx, 2 and 1/2 gives me negative 1/4 x minus 1/8 e to the 2x. So we have yp is equal to u1 y1 plus u2 y2 equal to e to the x times 1/4 x minus 1/8 e to the negative 2x plus e to the negative x times negative 1/4 x minus 1/8 e to the 2x. And this is yp is equal to 1/4 x e to the x minus 1/8 e to the negative x minus 1/4 x e to the negative x minus 1/8 e to the x. So e to the negative x and e to the x are already in yc. Don't need them in yp. So my yp is 1/4 x e to the x minus 1/4 x e to the negative x. Let's try and write that in terms of sinh or cosh now, since that's fitting with what we started off with. So let's first factor out the common factor of x. And let's pull out the 1/2 while I'm at it. So this is 1/2 e to the x minus 1/2 e to the negative x, which is 1/2 x sinh x for my yp. And then y equals c1 e to the x plus c2 e to the negative x plus 1/2 x sinh x. As I also mentioned before, it would be just as correct to have had your y1 be cosh x and your y2 be sinh x, and you would still end up with this. Okay, but you would have some identities that would have to do with hyperbolic trig functions that you are probably less likely to know off the top of your head than your regular trig identities. So I didn't work those in terms of the hyperbolic world. I just converted back into the world of e to the x and e to the negative x, and then converted back at the end to get a solution that looked like what you have in your book. This is like what you have in your book right here. Not that one, not that second one, but that second one is also correct, and you may find some symbolic calculators that are able to solve differential equations that might prefer to write answers in terms of sinh and cosh. All right, Let's go ahead and look at number 9 here. Y double prime minus 9y equals 9x over e to the 3x. So we're going to start with our auxiliary equation. So m equals -3 or m equals 3. So I have yc is c1 e to the -3x plus c2 e to the 3x. My Wronskian is e to the -3x, e to the 3x, -3e to the -3x, 3e to the 3x. So this is 3 plus 3 is 6. W1 is 0. 9x e to the -3x. E to the 3x. 3e to the 3x. So this is a -9x right here. And yeah, u1 prime is w1 over w, -9x over 6, -3 halves x. So u1 is -3 halves integral of x dx, -3 halves x squared over 2, then -3/4 x squared. Okay. And then W2 is equal to 0. And then 9x e to the -3x, e to the -3x, -3e to the -3x. This is 9x e to the -6x. And then we have W2 prime is W2 over W. It's 9x e to the -6x over W is 6. So we have 3 halves x e to the -6x. We're going to have to integrate by parts there. So u2 is equal to the integral. We have integral x e to the -6x. U is my algebraic part. dv is my exponential part. du is dx, and v is e to the -6x over -6, excuse me. So u2 is uv, so -1/6 x e to the -6x minus integral v du. So that's going to be -1/6 x e to the -6x minus 1 over 36, because that's going to be divide this by -6, e to the -6x. And then we're ready to find yp, which is u1 y1 plus u2 y2, which is equal to e to the -3x times u1 was -3/4 x squared plus e to the +3x times -1/6 x e to the -6x minus 1 over 36 e to the negative 6x. So we have negative 3/4 x squared e to the negative 3x minus 16x e to the negative 3x minus 1/36 e to the negative 3x. That's already in YC. I don't need that. So my YP is going to be negative 3/4 x squared e to the negative 3x. This, let me just check on this. I have the wrong fraction there. Let me see what I did wrong up here. UV. I forgot to multiply all this by 3/2. Be careful when you are you have a fractional multiplier out front like that. So this is negative 1/4 x e to the negative 6x. And this is 3 goes into there 12 times. And then 2 times that, so that's 24 e to the negative 6x. That changes. This is negative 1/4. This really doesn't matter. That one's still in YC, but that becomes a negative 1/4. So that looks good. All right. So y equals c1 e to the negative 3x plus c2 e to the 3x minus 3/4 x squared e to the negative 3x minus 1/4 x e to the negative 3x. Right? Moving along to number 11 from the textbook. Y double prime plus 3y prime plus 2y is equal to 1/1 plus e to the x. So our auxiliary equation, m squared plus 3m plus 2 equals 0. M plus 1 times m plus 2 equals 0. M equals -1 or m equals -2 gives me yc equals c1 e to the negative x plus c2 e to the negative 2x, giving me a Wronskian e to the negative x and e to the negative 2x, negative e to the negative x, negative 2e to the negative 2x here is equal to -2 e to the negative 3x plus e to the negative 3x is a negative e to the negative 3x. W1 is going to be 0, 1/1 plus e to the x, e to the negative 2x, -2 e to the negative 2x. is going to be 0 minus e to the negative 2x over 1 plus e to the x, like so, is a negative e to the negative 2x over 1 plus e to the x. u1 prime is w1 over w is going to be negative e to the negative 2x over 1 plus e to the x times 1 over negative e to the negative 3x. So I'm going to multiply top and bottom here by e to the 3x to get rid of this. That is going to give me that negative and that negative cancel. u1 prime is equal to e to the x over 1 plus e to the x. So u1 is equal to integral e to the x over 1 plus e to the x dx is ln of 1 plus e to the x. I don't need the absolute value bar since this is always positive, plus a positive number is always positive, so I don't need to force that to be positive. W2 is equal to absolute value bar 0, 1 over 1 plus e to the x. This is e to the negative x and negative e to the negative x here. So this Wronskian will be e to the negative x over 1 plus e to the x. That is going to be then divided by w to get u2 prime. Multiplied by e to the 3x, top and bottom. Move that there. And so this is a negative e to the 2x over 1 plus e to the x. Because the degree of the top is higher, I'm going to do long division here. E to the x plus 1 is my divisor. And negative e to the 2x plus 0 e to the x plus 1. Thinking of that as a polynomial in terms of e to the x, where that's e to the x squared right there. So this is going to be a negative e to the x, gives me a negative e to the 2x, and then that's minus e to the x plus plus. When I change my signs, e to the x, bring down the plus 1. This is plus 1 e to the x this is plus 0. Why did I write plus 1 there? Plus 0, plus 0. And this is 1 minus minus negative 1. That's minus 1 over e to the x plus 1. There we go. So that is going to be u2 is negative integral e to the x dx plus integral dx minus integral 1 over e to the x plus 1 dx. I need to multiply top and bottom here by e to the negative x. So that's going to be u2 is negative e to the x plus x. Go ahead and bring that negative on the inside here to help me. It's a negative e to the negative x over 1 plus e to the negative x. So that becomes u2 is negative e to the x plus ln of 1 plus e to the negative x, which I'm going to turn into a negative e to the x plus x plus ln of e to the x plus 1 over e to the x, just multiplying top and bottom by e to the x. Then I'm going to use my log properties here to write this as negative e to the x plus ln of 1 plus e to the x minus ln of e to the x, which is just x. 2 is negative e to the x plus ln of 1 plus e to the x minus x, and that minus x and that plus x zero each other out. So this is a negative e to the x plus ln of 1 plus e to the x. So now I'm ready for my yp is u1 y1 plus u2 y2. So my yp is had here e to the negative x was my y1. My u1 was right there, was ln of 1 plus e to the x. This is e to the negative 2x times negative e to the x plus ln of 1 plus e to the x. So yp is e to the negative x ln of 1 plus e to the x minus e to the negative x plus e to the negative 2x ln of 1 plus e to the x. And this is already in yc, so I don't need that. So my yp, I'm going to factor here e to the negative x plus e to the negative 2x ln of 1 plus e to the x. So my total solution y c1 e to the negative x plus c2 e to the negative 2x plus e to the negative x plus e to the negative 2x ln of 1 plus e to the x. All right, one more problem before we finish. I know we're running a little long here, but just want to do one more. And that is y double prime plus 3y prime plus 2y equals sine of e to the x. So auxiliary equation, m squared plus 3m plus 2 equals 0, m plus 1, m plus 2 equals 0, m equals negative 1, or m equals negative 2. So yc equals c1 e to the negative x plus c2 e to the negative 2x. W equals e to the negative x, e to the negative 2x, negative e to the negative x, negative 2e to the negative 2x. And we just did this last time, but we'll do it again. This is negative 2e to the negative 3x minus a negative is a positive, e to the negative 3x. So that's a negative 1e to the negative 3x. W1 is going to be 0 sine of e to the x. And you have e to the negative 2x, negative 2e to the negative 2x. So that's going to be 0 minus e to the negative 2x sine of e to the x gives us a u1 prime of w1 over w is a negative e to the negative 2x sine of e to the x over a negative e to the negative 3x. Negative negative will cancel. Multiply by e to the 3x top and bottom to get rid of this. So u1 prime is equal to e to the x sine of e to the x. So u1 is equal to integral sine of e to the x, e to the x dx. It's a simple u substitution that I'm not going to make, where u is e to the x and du is e to the x dx. This is sine u du. Comes out to be a negative cosine of u. So let's go ahead and find w2 now. Sine x, and this is e to the negative x, negative e to the negative x. So this is e to the negative x sine of e x, like that. And u2 prime is e to the negative x sine e to the x over w was a negative e to the negative 3x. So that is a negative e to the 2x when I bring that up, sine of e to the x. So we're going to integrate by parts here. u2 equals integral of, I'm going to split this up into a negative e to the x and a e to the, and a sine of e to the x, e to the x dx. I just split that e to the 2x into an e to the x and another e to the x. I say u is negative e to the x, dv is sine of e to the x, e to the x dx, which is what we just did last time. So that is a negative cosine of e to the x, and du is negative e to the x here, dx. So u2 is uv, so negative negative makes a positive, e to the x cosine of e to the x minus integral v du, so there's minus in the formula, minus minus, so it comes out to be a negative altogether. This is cosine of e to the x, e to the x dx, like so. And then this is u2 is e to the x cosine of e to the x minus sine of e to the x. So yp is u1 y1 plus u2 y2, where u1 was e to the negative x. I'm sorry, y1 was e to the negative x. Y2 was e to the negative 2x. And this was u2 is right here, e to the x cosine of e to the x minus sine of e to the x. And u1 is negative cosine of e to the x. So that makes my yp equal to a negative e to the negative x cosine of e to the x. And then we have a plus e to the negative x cosine of e to the x minus e to the negative 2x sine of e to the x. So these are exact opposites that zero each other out, making my yp equal to a negative e to the negative 2x sine of e to the x, making my total solution y equals c1 e to the negative x plus c2 e to the negative 2x minus e to the negative 2x sine of e to the x. That'll be the last one that I'm going to do for this section. There's plenty more examples to do, as well as some initial value problems and things that you can work out for this, but that gives you an idea of when you have to use this technique, why we don't use this technique all the time, even though it works pretty much all the time. There's going to be some other things that we're going to learn. Well, what happens if we don't have constant coefficients or things like that? And we have some special cases where we'll use some special factoring techniques, and then we'll have some other cases where we can't use those special factoring techniques that are coming up. But the next big section that we're going to talk about after this is actually going to be going back and doing applications of those linear differential equations and Hooke's law, some more circuits, and some things like that. So some spring motion problems and some circuit problems. So more examples of those things when we start to come back and talk about chapter 5. See you for the next video.